Now that we've seen the fundamentals of inheritance, we are ready to go into more advanced inheritance-related topics. In particular, there's a whole set of mechanisms that are really beautiful and powerful, having to do with the type view of inheritance. Remember that we have two interpretations of inheritance, one more module-oriented, the other one more type-oriented. And these mechanisms that we're going to see now, polymorphism, dynamic binding, and also their application to static typing, are all related to taking the type view of inheritance. Let's refer to our example of the previous lecture. All that we really need to remember is that we had a class public transport, which inherits from a class transport. And there were a few features that we are going to see again. I have here a variable t of type transport and a variable tram of type public transport. And the question leading to the notion of polymorphism is what we can do with these two variables, in particular how we can combine them in assignments. So one thing that we can do, and which is quite new as compared to what we have done so far, is this assignment of tram to t. The source is tram, the target is t. Now this is new because until now, when we were assigning something to something else, some source to a target, the target and the source had to be of exactly the same type. But now you can see that t is of a type, transport, and tram is of another type, public transport. Now, as you've already guessed, the combination is not going to be arbitrary, and of course it's not by accident that we actually have a class here that, for the source that inherits directly or indirectly. It could be a descendant of the class for the target transport. So what does this do? Does any object change shape? Do we have a transport object such as the one shown at the top here, which suddenly changes into, metamorphoses into a public transport object? No. Actually, no object ever changes shape in this kind of assignment. What's going to happen, and it's a natural consequence from things we have seen before in our study of assignment, is that it's going to be a reference assignment. Remember that if we have an assignment of a reference to a reference, then no copy of objects is involved. All that we do is that a reference which was pointing to a certain object now gets attached to, that's the more technical term for pointing to, gets attached to a new object. The only new thing here is that the original object that we had before, being attached to t, is of a different type from the object to which t will newly be attached. But other than that, there's no object creation, no object copy of any kind. It's just that a reference gets attached from one object to another object. So actually, this particular example is not that exciting because, you could say, why do this? If t is of type transport and now gets attached to to an object of type public transport, then that object was already known through another name, the name tram, which is more precise because tram is of type public transport. So by calling it t, which is really what this assignment is doing, we are losing information because we no longer know under the name t that it is a public transport object. All that t tells us is that it's a transport object, which could be, of course, as a special case, a public transport object. But really we're losing information as compared to what we knew before of this object through the more precise name tram. So this kind of assignment becomes really interesting when it's not certain. So consider a case like this in which we have some kind of condition, which of course is going to be evaluated only at runtime, so we don't know ahead of time whether it's going to be true or false. And then depending on whether it's true or false, we assign to t a reference to a tram object or a reference to a cab object. Remember that another descendant of transport was cab, okay, in our inheritance hierarchy. My picture is not very pretty, but it's to remind you of the shape of the inheritance hierarchy. So this becomes interesting, because then T is at the right level of abstraction as a name. What we know about T is that it's going to be some kind of transport object. And we don't know which one exactly it will be. In some cases, on Mondays it's going to be a tram, on Fridays it's going to be a cab, or to be more realistic, some condition might be a condition that depends on the user doing something. So there might be two pictures on the screen, one representing a tram, the other one representing a cab, and the user is selecting a mode of transportation for his or her next trip, and depending on where he clicks, T, the internal variable inside the program, is going to denote either a tram object or a cab object. It's going to be attached to one of these. So this is the kind of situation where such operations are interesting. These operations are known as polymorphic assignments. Assignment because it's an assignment. Specifically, it's always a reference assignment. This only works for references. And polymorphic because, as a result, you have a variable like T in our example that could become attached to objects of different types. Polymorphic, several shapes from the Greek, specifically here, several types. And as you can already guess, this mechanism of having assignments that are no longer monomorphic, that is to say with an identical type for source and target, but polymorphic, as you can already guess, this new possibility is going to open quite a few interesting horizons to us. It's going to give us much more flexibility than we had so far. Now we are going to have polymorphism, which means that we can assign a source of a certain type to a target of a different type, but of course the combinations are not arbitrary. You cannot assign a city expression to a person variable or the other way around. You cannot assign an apple to an orange. So actually what you can do is that you can have a variable of type fruit, and then assuming the obvious inheritance hierarchy, you can assign to that fruit variable an expression of type apple or an expression of type orange, assuming again that we have a class fruit from which classes apple and oranges inherit. So that's the general rule. It's that with polymorphism, we can have two different types for the source and the target, and they are not arbitrarily different. The type of source has to be a descendant of the type of target. Remember what descendant means. If we have a class, it's one of its own descendants. All of its heirs are also descendants, and so on. The heirs of the heirs, all the part of the hierarchy that is below A, that is to say classes inheriting directly or indirectly from A, are considered to be descendants. Now, at this point, we are kind of mixing the terminology between classes and types, and that's okay because our classes are types and our types can only be classes. A little bit later, we're going to introduce a distinction between classes and types when genericity comes in, and then instead of saying descendant, we'll say conform. But for the moment, we can the rule that I've given here is correct, and the requirement is that when we assign source to target, the type of source has to be a descendant of the type of target. This was for assignment. In general, in EIFL and other modern object-oriented languages, the rules are the same for assignment and for argument passing. That is to say, you have a routine like this one here, travel time, which takes a certain formal argument, T, okay, the name of a certain value that will be passed to the routine at the time of a call, and the value that we pass for the routine at the time of the call is going to be called the actual argument. So T is the formal argument, and the value that we pass in a form that we're going to see in just a second, but which you have already seen, is the actual argument. So the rules for associating an actual to a formal argument are exactly the same as the rules for assigning a source to a target. So in a case like this, the actual argument, tram, has to be compatible with the type of the formal argument t. And this is the case here, since tram is of type tram, and tram is a descendant type of transport. It's exactly the same as if we had the assignment t receives tram. So a couple more definitions, nothing new here, just precise definitions of the concepts that we have just seen. An attachment. By attachment we mean an assignment or argument passing. As noted, the rules are the same. An attachment is polymorphic if its target variable and source expression have different types. In the case of an assignment, this means the source and target. In the case of argument passing, this means the actual argument and the formal argument. An entity or an expression is polymorphic if it may at runtime, as a result of course of polymorphic attachments, become attached to objects of different types. And polymorphism is the set of these mechanisms. These notions also enable us to take a precise look at a very important concept of programming languages and programming in general, the notion of type, and in particular the notion of static type versus dynamic type. In the program text, we have entities, in particular variables. So I can declare x, for example, of type t. My x is not very beautifully drawn, but you can read what I try to write. And this is something that appears in the class text. Well, x is a certain entity, in this case it's a variable, and it's declared with a certain type. We call that type the static type of x. Why static? Well, it's because it exists in the program text, which is a static picture, as opposed to dynamic, which refers to what happens during execution of the program. And this opposition between static and dynamic is quite fundamental in programming. It's the distinction between what you read in the program text, static, and what happens during execution, dynamic. Now, at runtime, x, assuming for example that it's a reference, it's not expanded, x is going to denote in the sense of being attached to some objects. And some of these objects are going to be exactly of type t. So if I do create x, well, this gives me an object that is exactly of type t. So in that case, we say that the dynamic type, which is the type of this object, is identical to the static type. But now, with polymorphic assignment, we could have x receives the value of y, and y could be of type u. What is the relation between u and t? What is the constraint that we have on these two types? Well, as we've seen, u has to be a descendant of t, but u can be a different type from t. So in that case, as a result of this situation, x, which was previously attached to an object of type t, now becomes attached to the same object as y, that is to say, an object of type u. So you see the difference between the static type and the dynamic type. An entity can have only one static type, but it can have many dynamic types. The static type is unique because it is the type with which the entity is declared in the program text. But during execution, as a result of polymorphic assignments, the entity can become attached to objects of several different types, and so it can have many different dynamic types. We can apply these notions to the previous example. Nothing new here, just an illustration of the previous concepts. Remember that we had T of type transport, tram of type public transport. T, as a result, has the static type transport. And if the assignment shown here is executed, then at that particular point in the program execution, T will have the dynamic type public transport. Here's the rule that I asked you about a couple of minutes ago. The rule about the relationship between static and dynamic types. The dynamic type of an entity will always conform to its static type. Now, we said is a descendant, and now here I'm writing conform because this is the official language rule. I haven't defined conformance yet, but roughly speaking, for the moment, conforms is a descendant of. Now, this rule is not something that you have to prove for your programs because it's ensured by the type system, and if your programs do not satisfy it, then your program simply will not compile. So if you write something like my apple receives your orange, and the type of your orange does not conform, is not a descendant of the type of my apple, then the compiler is just going to send you back home to redo your work. So this is something that is guaranteed by the language definition and the compiler. The underlying notion is a fundamental one in programming and in programming languages. It's a fundamental weapon in our fight towards ensuring program correctness. It's the notion of static typing. A programming language is either statically typed or not. Examples of languages that are statically typed include Eiffel, Java, C#. Examples of languages that are not statically typed include things like Python, for example. C is in principle statically typed, but in practice not, because you can basically bypass the type system. So to define that a language is statically typed, we have to go through the three notions mentioned here. But the basic idea is very simple. It's that when the compiler accepts your program, then it guarantees that every operation that the program will execute during execution time makes sense. So, for example, if you have a variable p, and you have an operation move, and a call to p.move in your program, then the compiler will either accept or reject your program. But if the language is statically typed, then it means that if the compiler accepts this call, then it kind of gives you a guarantee, a promise, that for the object attached to P at runtime, there will be an operation called move. So P could be a person. Well, person, in the class person, there's going to be a feature move. P could be a tram. Same thing. In the class tram, there will be a feature move. But P shouldn't be a city, because as far as we know, cities don't move. And so if you mistakenly have a call like this with a target P that denotes an object for which the class does not have a move operation with the appropriate arguments, if any, if the compiler accepts it, then it guarantees that this is going to be the case, and that is what defines a statically typed language. So here's the precise definition: type safe call, then static type checker, then statically typed language. A call in an object-oriented program is said to be type safe if it is of the form x.f, such that the object attached to x has a feature corresponding to f. So this is a dynamic property. It's a runtime property. It's either true or not true at a particular point during execution. It could be true at one point in one execution, and it could be false in a later execution. In this example, I'm omitting the arguments. I'm not considering any arguments, but it's easy to generalize this definition to calls that can have arguments like x.f of a and b. So this is a dynamic notion. Let's now go over to the static side. We say that a static type checker is a tool, for example, a compiler, but it could be a separate tool. It doesn't have to be integrated in the compiler, that guarantees that for any program it accepts, then every call in every execution of the program will be type safe. It's a pretty strong guarantee, right? Because we have a single program text, we analyze it, we meaning the tool, and then if the tool says yes, then it's a promise that every possible execution of that particular call in every possible execution of the program will be type safe, meaning that the feature that we need will be found there. By the way, it's pretty easy to write a static type checker according to that definition. You can write a static type checker that rejects every program. And so it satisfies the definition because it guarantees that for any program it accepts, every call will be type safe. Well, sure, since it accepts no program. So this is kind of extreme, of course, and it's not realistic, but it does show to us that the issue in static typing is not only correctness, excluding unsafe calls, but it's also realism, because we can always ensure type safety by rejecting more. What we want is to rule out erroneous cases and still accept a powerful enough language or realistic enough language that people can write useful programs with it. And so that's the challenge in designing type-safe languages. It's to make sure that everything is safe, that there's not going to be any wrong calls, but on the other hand, that the language is powerful enough to accommodate really interesting programs. And this is why we're interested in techniques like polymorphism, polymorphic assignments, which give us more flexibility while still guaranteeing type safety. And so once we have defined the notion of static type checker, we can define what it means for a language like Eiffel or Java to be statically typed. It means that it's possible to write a static type checker for that language. In practical cases, usually the type checker is not a separate program, it's still part of the compiler. So when you compile your program, the role of the compiler is not just the basic role of generating machine code for your program, but it's also to check that everything's okay with your program and to refuse to generate code if it finds something incompatible, like the possibility of a type unsafe call. We've seen the basic inheritance type rule, which is that for a polymorphic assignment, X receives Y to be valid, the type of the source, Y must be a descendant of, must conform to the type of the target. Now, what do we mean by conformance? Well, we've given the basic value, the basic notion, which is that U has to be a descendant of T. And this is for non-generic cases. We have not seen genericity yet, so this is just to prepare for the future. And this is for reference types. Now, remember that we have two kinds of types, reference and expanded, and please remind yourselves of what the difference between reference and expanded types is. Well, a reference type has values that are references, enabling sharing. An expanded type has values that are objects directly. And for assignment, in the case of reference types, it's reference assignment. In the case of expanded types, it's just copying objects. And so as a consequence, polymorphism, as results from polymorphic attachments, is only possible for reference types. For expanded types, the source and the target have to be of exactly the same type. Now, it turns out that in Eiffel there is a mechanism known as conversion, which makes it possible to convert an object of a certain type to an object of a different type. Like, for example, you have an integer and you want to treat it as a real number, a floating point number, you can do this, but this mechanism is not inheritance, it's something completely different. So for conformance, and in particular for polymorphism, we are only talking about reference types. Now, this slide, I'm not going to comment it. Usually I comment absolutely everything on every slide. This is just to impress you. with what you'll be able to understand absolutely perfectly in a week or two from now. It's the full definition of conformance, which includes genericity. So you can take a look at it and try to guess what genericity is about if you like. You can look into the traffic software to find out a bit by yourselves. But for the moment, this is just fodder for future discussions. This is indeed all that we had to see in this sub-lecture. So what we have studied is a set of really important techniques that are fundamental in modern programming. We've seen more properties of inheritance, not so much on the module side as on the type side. We have seen conformance, which is a relation between types, and so far it means the same thing as a class being a descendant of another. We've seen the possibility of assignments that are no longer just monomorphic but polymorphic. An entity declared of a certain type T can become attached to objects of other types, but not arbitrary types. These have to be conforming descendants. And static typing is the other fundamental notion that we've seen in this lecture. It means that the language guarantees the avoidance of type unsafe calls, and in the case of polymorphic assignment, to achieve static typing, the type of the source of the assignment must conform to the type of the source of the target. We still have a bit more to see about inheritance, and this will be for the next sub-lecture.